Hello everyone, welcome to EEEE lecture number 43D. So today we will discuss about the transformer ratings. So there are two types of ratings for the transformer, voltage rating and kVA rating. So voltage rating, it indicates the normal or the rated primary and the secondary voltages. For example, if the voltage rating is given as 200/400 volts, that means that the primary rated voltage is E1 approximately equal to V1 is equal to 200 volts, and the secondary rated voltage is 400 volts. In terms of kVA rating, during the operation of the transformer, power losses takes place in the winding and the core. These power losses appear in the form of a heat, which increases the temperature of the device. Therefore, the output of the transformer is expressed in kVA rating. kVA stands for kilowatt ampere. The rated transformer output is limited by heating, hence losses in the transformer are copper and the core losses. These losses depend upon the voltage and the current and are almost unaffected by the power factor of the load. Therefore, the transformer's rated output is expressed in kVA and not in kilowatt. Because in case of single phase supply, power in a single phase is given by the formula VI cos phi. So this is the active power. Whereas in case of apparent power, is denoted by S, we have only V into I. And that is the rating over here, that is VA, kVA. This is in watt. So that is why this has been preferred. Okay. So that's the reason why the transformer rated output is expressed in kVA and not in kilowatts. This is not expressed in kilowatts. This is kilowatts. It is expressed over here because it has no accountability for cos phi, because it's unaffected by power factor of the load. So that's why we go for apparent power, that is V or kVA rating of the transformer. So this kVA rating is given by E into I1 of E1 into I1 of full load divided by 1000, E2 into I2 of full load divided by 1000. Now why do we divide by 1000? I'll let you know. So basically V is written as E1 because it's the primary transformer rating, and I1 at full load. Okay, if this you measure in V into A, it's normal VA rating, right? Now if I want to measure in kVA, I have to, I mean this is 1000, right? So I have to divide by 1000. So that's why E1 I1 full rated divided by 1000. Now this is same as first only. Alright. So that's why kVA rating will be equal to E1 I1 at full load divided by 1000 equal to E2 I2 at full load divided by 1000. Where I1 full load is the full load primary current. I2 full load is the full load secondary current. Now from the kVA rating we can calculate the full load current on the primary and the secondary. So from this formula itself, I1 full load will be given by kVA rating into 1000 divided by E1, and I2 full load will be given by kVA rating into 1000 divided by E2. So that's all about the rating of the transformer. Always in summary remember, transformer ratings are represented in kVA and not in kilowatts. Now the next topic is voltage regulation of the transformer. Now ideal transformer, for an ideal transformer, the voltage rating is, voltage regulation is zero almost. So for an ideal transformer, the voltage regulation is 0%. Whereas for a practical transformer, it is not zero. It is close to zero, but it is not zero. So let's see why this happens and what's the definition of voltage regulation. So when a transformer is loaded, that is it is connected to a load, resistive, inductive or a capacitive load, the secondary voltage reduces. This is due to the fact that there is a voltage drop across the secondary winding resistance and the leakage reactance. Alright, so let me show it to you. So let's say this is my primary side of the transformer and this is the secondary side of the transformer. Now let's say it's connected to a load right? This is the load L. This is the secondary voltage. This is R2 X2. This is my primary voltage V1, which is AC in nature. Now, uh, the secondary voltage V2 is not same as E2. E2 is the mutually induced EMF, because whenever the current flows through this R2 and X2, there will be a voltage drop. Okay, so that is what we are saying. The voltage drop exists because of the secondary winding resistance, which is R2, and the leakage resistance, which is X2. So this is your R2 and this is your X2. Alright. So this change in the secondary voltage from no load to full load condition is expressed as a fraction of a no load secondary voltage. Alright. And this is called as a regulation of a transformer. So how do we define percentage regulation? Percentage regulation is secondary voltage on no load, which is E2, because when we don't connect it to any load, E2 is equal to V2. Alright. So the secondary voltage on no load is E2, right? So secondary voltage on no load minus secondary voltage at full load condition, which is V2, divided by secondary voltage on no load, that is E2. So percentage voltage regulation is E2 minus V2 upon E2 into 100. Alright. So now this E2, the mutually induced EMF, depends upon the magnitude of the load current and the nature of the power factor. Alright. The voltage regulation is the figure of merit of a transformer. Smaller the voltage regulation, better the performance of a transformer. So I hope this topic is clear. So you have to know what is voltage regulation, its definition, and its formula in terms of percentage. Now, let us derive the expression for this voltage regulation. Let us draw the simplified circuit, equivalent circuit of a transformer. You remember in the last to last lecture we have discussed about RO2 and XO2 being the, this is the approximated equivalent circuit, simplified one. So where the primary side parameters have been transferred to the secondary, and secondary side parameters are RO2, XO2 and ZO2. This we have discussed before, right? Where RO2 is R2 plus K square times R1, XO2 is X2 plus K square times X1, ZO2 is square root of RO2 square plus XO2 square, and so on. So this is a simplified circuit of a transformer with resistance and reactance referred to the secondary winding. Now if we want to draw the phasor diagram of the secondary side of the equivalent circuit for a lagging power factor, so we will have this equation over here. E2 bar is I2 RO2 bar plus I2 XO2 bar plus V2. So with the help of this diagram, we have to draw the phasor diagram and hence calculate the expression for the voltage regulation. Now, first we start with a reference point over here. So first we draw E2. Okay, so this is the first thing. Then since it is a lagging power factor, I2 is lagging behind the voltage. Alright. Now from V2, we have to draw I2 RO2. Now I2, you draw a parallel vector like this to I2. So I2 RO2 will come, and then I2 XO2 will be 90 degree leading. Okay, so I2 XO2 should be 90 degree from I2 RO2. Alright, and then the I2 RO2, I2 XO2 and V2, the phasor sum will be E2. So the vector sum E2 will be I2 R2 plus I2 XO2 plus V2. Alright. So this is the phasor diagram for the secondary side of the equivalent circuit. Secondary side of the equivalent circuit. Now, in order to find out the approximate formula for voltage regulation, the following phasor diagram is modified as follows. Okay, so let me explain. So what we have did, we have drawn till O, till E2, V2, I2 RO2 and I2 XO2. Now all these dotted lines is the extra tough. So you take O as the origin, take a protractor and draw an arc CM. Okay, let me mark this point as C and let this mark this point M. Now extend this point, I call it A, extend this to dotted line M, right? Then draw perpendicular from C to down, okay, till L, and draw a line BL over here in dotted line. Also draw perpendicular BD, parallel perpendicular to the line AM. So these are the following things we have added: A line AM, line AN, BD, BL, and CL. Alright, so this is the modified phasor diagram. From the geometry, we will find the value of total percentage regulation. So what's the total voltage drop? So total voltage drop according to the formula is E2 minus V2. So we need to find E2 minus V2. So according to the circuit, E2 minus V2 is actually OC minus OA. Now OC minus OA is actually equal to OM. It's equivalent to OM minus OA according to the diagram. Okay, according to the diagram, it's basically OM minus OA. All right, here it is OM minus OA, but over here that is equal to AM only. Okay, E2 minus V2 will be just equal to AM. Okay, see, OM minus OA is AM. Now AM is actually two components, AN and NM. Now NM, as you can see, is very small. So E2 minus V2 voltage drop is just AN. Now AN is again a component, two components, AD plus DN. Now DN can be parallel to BL. So AD plus BL. We have to find out AD plus BL. Now what is AD? Now if you see this triangle, small triangle, this is I2RO2. So AD will be the X component, which will be I2RO2 cos phi 2. So this has to be cos phi 2. Alright. This is phi 2. This is also phi 2. So AD line will be I2RO2 cos phi 2, and BL. You can see this triangle over here, I2 XO2 BL and CL. So the X coordinate over here is again, here this one is I2 XO2 sin phi 2. Okay, so BL is I2 XO2 sin phi 2. Now these things we add over here. So the percentage voltage regulation is E2 minus E1, and E2 minus E1 is I2RO2 cos phi plus I2 XO2 sin phi divided by A2 into 100. So this is the percentage voltage regulation for lagging power factor. Similarly, for a leading power factor, it can be proved that the percentage voltage regulation will be same as this, but there will be a minus sign in between. So in general, the percentage voltage regulation will be given by I2RO2 cos phi plus or minus I2 XO2 sin phi divided by E2 into 100, where plus stands for lagging power factor, minus stands for leading power factor. So yeah, this completes the discussion on the percentage voltage regulation. Now let's discuss about the efficiency of a transformer. It's given by eta. Now efficiency for any device is the ratio of the output power to the input power. So eta is output power upon input power. Input power is same as output power plus the total losses, and the total losses consist of copper losses plus iron losses. Copper losses are written as WCU, iron losses are written as WI. So eta is output power divided by output power plus copper losses plus iron losses into 100, because it's a percentage efficiency. So if I write over here, this is percentage efficiency. Okay, alright, let me save this file. For transformer, the output power is given by V2I2 cos phi 2. Okay, and if I want to write in kilowatt, I have to divide by 1000. And cos phi 2 is the power factor, and V2I2 divided by 1000 is in kVA rating. So output power is kVA rating into power factor, which is in kilowatt. Okay. Now copper losses WCU is actually, we have seen before, it is I2 square into RO2. We have seen at the start of discussion what is RO2, and iron losses is WI. So percentage efficiency is given by V2I2 cos phi 2 divided by V2I2 cos phi 2 plus WI plus I2 square into RO2. Alright, so let's call this equation number 1. Next we will discuss the condition of maximum efficiency. Now this is a graph of efficiency versus the load current I2, right? So the load current at which the efficiency attains the maximum value is I2 max, and the maximum efficiency is eta max. Now from equation number 1, if we differentiate this equation number 1 with respect to I2, we get the following. Okay, so differentiating both the sides with respect to I2, we get, this is equation number 1. and let's call this denominator as V and numerator as u. So du by d, it's a rule of division. So d by dx of u by v will be v du by dx minus u dv by dx upon v square. So similarly, we have to apply over here v. We have to write as it is. We have written as it is into du by dx. So this is u. So v2 I2 cos phi 2. Differentiation with respect to I2 will be I2 will be gone. So it will be v2 cos phi 2 minus u. So u is v2 I2 cos phi 2 into differentiation of with respect to I2. So if I differentiate v with respect to I2, I'll get v2 cos phi 2 plus wi plus twice I2 RO2. So that's what I've written over here. Yeah, Wi basically the iron losses are not a function of I2, so that's why they are constant. So that's why the differentiation of a constant is 0. That's why we have not added that term over here. So point to be noted that divided by v square, and that is v square. Now for maximum efficiency, we have to equate derivative of d eta by di2 should be equal to 0. That means this equation we have to equate it to 0. That means denominator goes. So this term will be equal to this term then. So v2 I2 cos phi 2 plus wi plus I2 square RO2, the whole into v2 cos phi 2 is equal to this term. From here we see v2 cos phi 2 gets cancelled. And if you open the bracket over here, v2 I2 cos phi 2 plus wi plus I2 square RO2 will be equal to v2 I2 cos phi 2 plus twice I2 RO2. Now if you cancel out the common terms, you get wi is equal to I2 square RO2. And we know I2 square RO2 is copper loss. So therefore, the condition to achieve maximum efficiency is that whenever the copper loss is equal to the iron loss, maximum efficiency is attained by the transformer. So that's what we have written over here. Therefore, when the copper loss is equal to the iron loss, the efficiency of the transformer is maximum. Alright. Let's calculate the load current at maximum efficiency. So for eta max, I2 square RO2 is Wi, right? But I2 is equal to I2 max when eta is equal to eta max. So I2 max square into RO2 is Wi. So what is I2 max? I2 max will be equal to Wi upon RO2. So this is the value of the load current at maximum efficiency. And the unit is amperes, of course. Next, we will write the formula for the maximum efficiency. Now output power efficiency is defined as output power divided by output power plus copper loss plus iron loss. Now we know at maximum efficiency what is the condition? Iron loss is equal to copper loss. Also output power, we have written it before, is represented by kVA rating into power factor. Okay, so we can write maximum efficiency is given by kVA rating into power factor divided by kVA rating into power factor plus twice Wi, because Wi is equal to the copper loss. Alright, so this is the formula for the maximum efficiency, and with this we have come to the end of the module of transformers. So thank you all for joining. Have a good day.